Hello, everyone. Let's talk about topic 9, and we'll kind of take it from there. It's about fluids and solids, and how fluids and solids act, I guess, in the physical universe in which we find ourselves. We'll talk about the states of matter. We'll talk about density and pressure, the buoyant forces and Archimedes Principle, fluids in motion. Except there's a good amount of stuff here. It shouldn't be too bad. Let's figure out exactly how we want to go with this when we do talk about it. So essentially, they talk about there are 3 states of matter for topic 9. The summary goes pretty good. I go pretty close to the summary, you guys, and then I'll go a little bit further as well. For topic 9, they talk about states of matter initially, or at least that's the introduction, states of matter. Matter is normally classified as being in one of 3 states, solid, liquid, or gaseous. The 4th state of matter is called a plasma, which consists of a neutral system of charged particles interacting electromagnetically. So as a system itself, it's neutral, but there's charged particles and they are interacting electromagnetically. So they talk about density and pressure as well, and let's talk about some things that we can say regarding that, and we'll figure it out. They give the Greek letter rho to mean, and they put, I guess when they define stuff, they put 3 things here, meaning definition. It's mass divided by capital V, which is volume. Mass divided by volume is mass density. I've heard the expression sometimes weight density, which is in terms of newtons, the weight of the object in a particular gravitational field divided by the volume. Well, in this case, that's not the case. It's just mass divided by volume. That's what rho is. So keep that in mind. Pressure, the pressure being a fluid measured in this thing called pascals, is the force per unit area that the fluid exerts on an object immersed in it. So again, they put, I've seen that, I've not always paid too close attention to the way the book says stuff. This P is not the same as this. This looks like a P, but it's the Greek letter rho. This is the Greek letter rho. That looks like a P, but it's the Greek letter rho. This is P, Latin-based P. And they're saying pressure is force exerted perpendicular to an area of area A divided by A. Force divided by area is the pressure. And they put those 3 things down there like this, and it's good. It makes sense. I've seen this before. I've had students of mine in other places actually, when they've studied in different countries, they really make that point to say an identity. It's identical to that. So it's kind of neat in that regard. But just a fancy equal symbol. There's no negative sign here. That's the one thing that kind of gets me on that. But so later on when I start writing, I'll probably just write it like this, you guys. Rho equals M over V, and P equals F over A, and kind of leave it at that. I think this might be introducing something that might be more confusing for you than helpful. Anyway, let's leave that there. Be aware of the subtlety that's going on in that regard, guys. They talk about a couple things here, guys. Let me kind of move around within the chapter itself, and I'm always kind of debating with myself how to discuss this. I mean, there's ways to do a lot of this stuff, and you'll see in like other, let's put it this way. You'll see in other videos for the particular chapter. I might not give too much of a discussion on this thing. Here I'll try to give more of a discussion of what's going on and kind of take it from there when we do it. And we do have many problems solved here on Canvas, and we got 2 problems that are also, I think 2 or 3, don't have it in front of me right now. In fact, I do have it in front of me. What am I talking about? There's just 2 problems that I actually done on film, but there's many problems pertaining to this stuff that you're going to find elsewhere. Okay, let's see. We'll just do a few things here, and we'll figure out what we want to say. They are saying there's more pressure if you are a swimmer or a diver or a scuba diver, and you snorkeling, if you go under the water deep enough, you guys, you are feeling a lot of pressure. If you go deeper into the water, you're feeling even more pressure. So there's something going on here. And, I can write it, and we can derive it, we can figure out what's going on here. So I'll read it to you a little bit, and we'll kind of take it from there. Variation of pressure with depth. The pressure in an incompressible fluid varies with depth h according to the expression P equals P0 plus rho GH, where P0 is atmospheric pressure. They write that differently. Sometimes I write piece of atmosphere. A lot of times we talk about, because right now we're experiencing atmospheric pressure. It pervades the earth, thankfully, and we can breathe because of it. There's air and we can breathe, and there's breathable air, and there's pressure that allows us to create a pressure differential. There's a pressure on the outside, there's a pressure differential we can enact, we can actually do, we can make happen, and that allows air to rush into our lungs, and we are nourished with air. The pressure is a particular depth. It's P0 plus rho GH. P0 is P atmospheric pressure. P atmospheric pressure, there's a unit of measure for that. We call it 1 atmosphere of pressure, which is equal to 1.013 times 10 to the 5th pascals. What's a pascal? 1 pascal is 1 Newton of force exerted onto 1 square meter. 1 Newton of force exerted onto an area of 1 square meter. So we have this right here. So that's going to be 1 point. There's a lot of ways to write it, guys. As long as we're cognizant of what's happening, we don't have to repeat this too much and deliver the whole speech over and over. But it's looking something like this. 1 atmosphere is the same as this, same as this. So let's see what we got here. Let me just check on this real quick, guys, just to be on the safe side here. We should be okay though. A lot of this stuff you try to do on memory, and you hope you're okay. Just want to make sure I don't tell you something totally crazy here. Life of me, I can't find. You turn the page and it's always present. I'm absolutely sure this is right, but I want to make absolutely sure, for sure, that I'm right on this. I knew, let me see. Safe, just in case. Well, this is very odd, guys. Usually I open the book, if it's pertaining to this stuff, you open it to one place, and yeah, there it is. 1.013 times 10 to the 5th pascals. I knew that was right, but man, it's a crazy endeavor sometimes. I mean, you want to make sure it's. I knew that was on, but I still want to make absolutely sure it was on. Yeah, it's fine. It's fine. So you're looking at this. They're giving you here this conclusion will tell you what the pressure is. What's going on here? If something is submersed in water, there's a lot here. I mean, there's a lot here, so let me try to, you got, this is a fluid. This is atmospheric pressure, P0, which is P atmosphere. P0 is P atmosphere. Well, look, guys, you are experiencing atmospheric pressure right here on Earth. As we sit here, as we stand here, as I go outside for a walk or something like that, there's atmospheric pressure. For our purposes, it's constant. It's one atmosphere of pressure, which is the same as, 1.013 times 10 to the 5th newtons per square meter. What is that? That's about 101,300 newtons, a little more than 100,000 newtons for every square meter. You wouldn't think that's going on. Well, yeah, you've been living it your whole life, so you don't really know, but it's there. Obviously, when you are a scuba diver and you go under the water, you're still experiencing atmospheric pressure. What do you mean? I'm not in the atmosphere anymore. Yeah, I know, but the atmosphere is right above you, and it weighs down right on you. The weight of the atmosphere is still on you. It weighs down right on you, so it's never leaving. The weight of the atmosphere weighs down on you. In addition to that, something denser called water weighs down on you also. That adds to the pressure that you're going to experience. It adds to the pressure that you're going to experience. So, there's some pretty interesting stuff here, guys, regarding that. So if there's a block in here, and it's at a depth of H. Why am I putting the bottom as the depth? Because before I put this into the water, the block was up here. The block was up here before I put it in the water, and then I brought it down. I brought this bottom guy down. I brought this bottom guy down to a depth of H. I brought the top guy down to a depth of H. So you got to start somewhere. So when you talk about depth, just be consistent. I'm going to say the lowest point of the block is the depth, is where I'm going to measure the depth to bring it down. So that's where this guy is right there. So let me try to write this. I mean, I don't know, arguably I shouldn't even erase it, but okay, so we got this right here, as we said, and if you got this guy, it's this little, here it is, then bring them down. And you got the pressure, of course, pressure going straight down, as we said. All right. Where are we drawing? How are we drawing this conclusion? Let's make a couple things straight. They talk about an incompressible fluid. And incompressible fluid is, for our purposes, a fluid that you're not going to, look, I mean, you name it, in physics, a lot can be done, and a lot happens in extreme conditions. I mean, we're talking about black holes. I mean, there's things going on there that are literally out of this world kind of thing, It's the physics of the universe at an extreme level, I guess you could say, and they're still trying to figure out a lot pertaining to it. So, okay, there's a lot of extreme things that can happen. Regarding what we do on Earth is, if I have a container of water that's very, very strong, container of water here, it's very, very strong, and I put a piston that fits perfectly over the container, and I try to push down the water, I can't really compress the water any more than it is. If the water is, if it's 1 cubic meter of water, a meter by a meter by a meter. If it's 1 cubic meter of water, I can't, in our circumstances with which we're dealing every day, in the physics of the practicality of life and the everyday life that we're dealing with, I'm not going to compress that water. So it's incompressible. Air is compressible. However, we're going to get into some physics where you can kind of you can kind of do some things, you can kind of make certain assumptions, and things work. When I get into Bernoulli's equation a little bit later, you'll see what I'm talking about. Okay? So, we'll cross every bridge as we need to cross it, I guess you could say. All right. So we're right here, we got something like this. This guy's got, there's a lot here. Now, and what I do want to say is, let's say it's a cube or it's a rectangle, it's a cube or a rectangular box. What I'm about to show you, I can't prove it to you, I don't have the time to prove it to you, but what I'm about to show you holds for any shape object. You can give me the most bizarre shaped object that you want, and what I'm about to show you holds even for that. How can you do that? Because I can break up bizarrely shaped objects and make them into the summation of infinitesimal rectangular shaped objects. I can make any object into the sum of very many infinitesimally, I can take any object and make it into the sum of very, very many infinitesimal size rectangles, or for area, rectangular shaped boxes for volume. So there's a lot you can do here. We got to talk. Whenever something is in, like I said, there's a number of ways you can go. Let me kind of go more or less in a summary of this thing. I'll kind of stay faithful to the summary of this, and then jump around a little bit with it. They're basically saying, guys, that the pressure, if you immerse something in other words, if there is, at this height, there's pressure against the wall right here. There's the same pressure at the same depth against the wall over there. Also, there's the same pressure pushing up, same pressure pushing this way, same pressure pushing that way when we're doing this. In other words, pressure is not a vector, it's a scalar quantity, and at a particular depth, the pressure that is the pressure, if anything is right here, it's going to experience, I guess maybe a better way to say this, guys. I mean, it's essentially the same thing, but certainly I think a better way. My fault for not. There was an object right here. Let's say it was really, really small, so let's not worry about the depth too much. The pressure experienced right here is the same as the pressure experienced there, the same as the pressure experienced there. They're all equal pressures right there when this is happening. If it's just a point, don't even make it an object, make it a point. True, at any depth, the pressure equally distributes itself throughout. If you were to put a piston on top, of this thing and press down, and let's say there was outlets here for the stuff to move somewhere or whatever, if you increase the pressure this way, pushing downward, that pressure will manifest itself, will distribute itself, that increase in pressure will distribute itself throughout the fluid. The pressure will distribute itself throughout the fluid. I gotta talk to you. There is a pressure right here. Trying to think good. There's a pressure the water exerts and the atmosphere exerts right here. Now it's the P0 is present everywhere. It's hitting everybody. But in the water itself, there's a pressure here, and there's a greater pressure there. If one arrow looks bigger than the other, it's supposed to. The deeper you go, the more pressure that is being experienced. This right here, they're saying a depth H. You could do a bunch of things here. Let's call this Y. Let's call this area at the base area A, which is the same as the area of this guy. It's area A2. Let's talk. right here, if P equals F over A, if P equals F over A, then F equals PA. That's P, not a rho. That's F equals PA. So, there's a pressure here, and this gets interesting. There's a pressure, there's a force, there's a whole lot going on here. So we got this kind of in the back of our mind when we're doing this. Can I talk to you a little bit, guys? If that's A, and this right here is A, in terms of area, I guess I'd like to know how much pressure is being exerted. So you're looking at something here. You can say, okay, there's a buoyant force and a whole lot going on. Trying to see exactly what I want to say here with this. So we would actually say, regarding something like this, where the pressure is, even if the box, okay, there's a box in here, we said something here. Let's say the box, it can have a mass, it can not have a mass, that's not a big deal. Let's put a box right here, but let's make the box almost imaginary. Let's say, okay, what are you talking, man? Now you got an imaginary box you're putting on here? Yeah, in a sense I'm saying I'd like to see what's going on with these pressures. What's going on with this whole thing? How much push is going on? Well, at this height right here, there is a box of water above right here. There's a box of water above right here, and it is weighing down straight down. It is weighing down straight down. There's a box of water. Now, this is just an imaginary box right now. Later on, we'll do other stuff with the box, make a real box. Maybe this is a bar of gold. I want to find what the buoyant force is. I want to talk about a lot of stuff that way. But for right now, say it's like a kind of imaginary bite. The thing you drew here, you can kind of draw it here, and it's still imaginary. And I just want to see what's going on here. What kind of pressure? What's going on in terms of pressure differentials, whatever. We know that at this depth right here, which would be h minus y, just trying to think of good numbers to put here, guys, when we're doing this. Maybe leave this here. I may want to draw this again and do something else with it. Let me just try to think how I want to say this exactly. Let's do this. Let me draw this again, but leave that there. I'm going to need that there. I just think you're in better shape if I bring this guy down to here, let's say, and I want let's say I was right here, and there's a box, same box. And I'd like to know what kind of pressure is at this depth. And I guess I could call this guy, do a lot of stuff here, I guess, guys. The symbolism here can get a little messy. Let's call this Y1. Let's go all the way down to here. Let's call this Y2. And, so it's a box, so I don't want to draw a box here. It's the same box as that one. Now I'm just bothering to draw it, I guess. Maybe that's a good idea, maybe it isn't. I guess we'll soon find out. That's A as well. This is y, I already said that, so I'm staying consistent with the box here. That box, I'm just giving you a straight side view. Here, I'm giving you a 3/4 view of it. Maybe good, maybe bad. What is the pressure at that particular depth? Well, that's a great question. It's a great question. Does everybody agree that there is all this water above the box? There's a whole cube, there's a whole rectangular box of water on top of this rectangular box. Great. So what? The force the water exerts is the weight of the water period. It's the weight of the water. It's the mass of the water, times that. I'm going to ask you a question. Isn't rho mass divided by volume? Isn't mass the volume of water above it times rho? That's the force above it. Why is this thing above it? Well, because you immerse the box in the water. Here's the box, or imaginary box, doesn't really matter much. I just know there's water above it. If I put my body underneath that column of water weighs down upon me. How much? mg, which is the same as rho v times g. It's the same as rho v times g. That's the force I'm experiencing. Really? Yeah. Is the pressure force divided by area? It is. Is rho, again, the rho's and the p's, right? Watch out, right? Everybody okay with that? I keep asking that and nobody's in here. It's just myself and the camera person. So, all right. P equals rho Vg divided by A. I got a question to ask you. Isn't this guy right here the height? Y1? I mean, the whole thing, forgive me, the whole thing here, that's Y1, I call this Y2. Y2 is equal to H, according to that scenario over there. But I got this. Can you talk to me here? What is this volume right above it? What is this volume right above it? I'm going to go over to this board. I'm not going to erase this stuff yet. Pressure at depth Y1, but at any depth, guys, just happens to be at Y1 right now, is F over A. We said that was mg over A. We said that was rho Vg over A. Rho is rho. Is V A times the height? The height happens to be Y1. Divide by A on each side. Y1 happens to be the depth on top. Y1 happens to be the depth on top. Y1 is the depth on top. Y2 is the depth on the bottom. So you could do the exact same argument, ladies and gentlemen. And you could say, well, P1, the pressure on top is rho g Y1. The pressure on the bottom is rho g Y2. One goes down, one goes down. Now there's a pressure going up. There's a smaller pressure going down. This is P2, this is P1. So the difference between the two, I guess it's unbalanced, isn't it, guys? Look. If one arrow looks longer than the other, it's supposed to. The deeper you go, your ears pop. More pressure. We got this. That's crazy. What's going on here? There's a difference in pressure here. Delta P equals P2 minus P1 equals this minus that, which is rho g Y2 minus Y1 rho g Y2 minus Y1 we said is Y. It's the thickness of the rectangular box. And I already told you I can make this work for every box. We can make this work for every single box that's there, you guys. Fascinating stuff. We can make it work for every single box that's there, every single object that is there, I can move it around and make it a whole bunch of tiny boxes comprising that amorphous solid. It doesn't have to be a pretty solid. All of this physics applies for any solid that you put in there. I can break up any solid and make it into the sum of almost an infinite number, or practically an infinite number of small boxes to kind of describe that solid. I can make everything into a sum of rectangles. I can make everything into a sum of rectangular boxes. For area, I can make things into a sum of rectangles. It's calculus, a lot of calculus right there. And I can make, in terms of area, I can make everything in terms of all areas. I can break them up into a sum of rectangles. When we're talking about areas, when we're talking about volumes, I can break up all volumes and make them into a sum of rectangular boxes. So rectangles and rectangular boxes, if they're small enough, and if I have enough of them, if I have many of them, I can break up all the areas. I can describe all areas as the sum of rectangular boxes. I can describe all areas as the sum of rectangles, very, very small ones and very, very many of them. And I can describe all volumes as the sum of small rectangular boxes and very, very many of them to accomplish that task. Important stuff, and we can use this a lot. I'm going right here. Y2 minus Y1 is Y. That's the change in pressure. Tell you what I'm going to do. If you were to multiply by A, if you were to take delta P, the change in pressure, and do a lot of ways here. Not sure how comfortable you can feel with it. I can argue this a bunch of ways with you, so I want to make sure you're okay with it. You guys understand that we've said a lot of stuff. We've said pressure is force over area. Force equals pressure. Force equals pressure times area. So, if you multiply this guy by area, you got a force. You multiply this guy by area, you got a force. Subtract the two, you got the net force going upward, called the buoyant force. Let's make it happen. Pressure times area. Let's talk about that a little bit. If you subtract the two, it's the resultant force. It's force resultant, and they call that the buoyant force. F sub B for buoyant force. Subtract these two, and you end up getting rho G. There's a lot here, guys. A y2 minus y1. y2 minus y1 is, so let's see here. Rho G A Y. All right, this is pretty fascinating, if you ask me. That's A. All the way down is Y2, partially down is Y1. Y2 minus Y1 is Y. What is area A times Y? It's the volume of the solid. It's the volume of the solid. Do I need to move this, Christine? Are we okay? Do I need to move that at all? No, okay. All right. They call this the buoyant force, ladies and gentlemen. You put anything in any fluid that can, let's just leave it at that. I don't want to get into all what if scenarios and everything. You put anything into a fluid, there is a buoyant force exerted on it. And we got this. There's a buoyant force. The buoyant force is rho GV. I got to talk to you. Got to talk to you. You got to be really careful here. That's true. That is true. I'm coming here to the front here. That's true. But you better qualify it. I better get chalk that writes, actually. Actually, I gotta learn how to write with chalk, I guess. FB equals rho of the fluid. Rho of the fluid times G times V. FB equals rho of the fluid, G times V. The fluid that is displaced, the amount of fluid that is displaced, determines the buoyant force. What does that mean? If I put a very, very light box that can't be penetrated by the fluid, if I put a very, very light box into some liquid that is very dense, like mercury, the displaced amount of mercury will push very hard to bring this thing to shoot upward, give it a buoyant force. If I put it inside of, not mercury, mercury's very, very dense, like, I don't know, 11, 12 times more dense than water. But if I put it in something as dense as water, or even less dense, there's still going to be a buoyant force, but not as much. It's the fluid. It's not the density of the object. It's the fluid for the buoyant force. Well, okay, guys. True. Where are they getting this? And like I said, guys, this whole idea, it's the volume of the fluid displaced. It's the volume of the box, and the volume of the box is the volume of the fluid displaced. So they write it pretty good. There's this thing called Archimedes Principle. He was a great Greek mathematician that lived, I think, I don't know all of his life, but he lived probably a lot of his life in Syracuse, Sicily. There's even, I think there was a stamp, I don't know if it's still the case, I think we looked it up one time. There's an Italian stamp that's got Archimedes on the stamp. It's kind of neat. You make it on a stamp, you did something. You did some good work, I guess, to get there. So they regard Archimedes as the three greatest mathematicians, at least in the Western world. And frequently the perspective they're giving is from the Western world's perspective, but only from that perspective. In regard to the Western world, the three greatest mathematicians are frequently mentioned as Archimedes, Gauss, and Newton. Archimedes did a lot of stuff. I think he did elements of calculus as well, among the first to have done so. So there's a lot of cutting-edge stuff that was done by these mathematicians. Not one of those mathematicians didn't stand upon the shoulders of giants. There is no great accomplishment, no great scientist, no great mathematician no great anybody who hasn't stood on the shoulders of others. You had to. We all do. You know, to accomplish what we try to accomplish. You got to know that. There are also great mathematicians, obviously, in the Middle East, in Africa, China, what now is Latin America. All over the world there have been brilliant, brilliant people, many of whom you'll never even, tremendous numbers of whom you'll never even know about. You know, so always that has to be kept in mind. Always that has to be kept in mind. So this is essentially Archimedes' principle. Archimedes, I guess, was taking a bath one time, they say. And he jumped in the tub, and when he did, the water came out. And he realized that even though he's not a cube or a sphere or whatever volume his body had, threw that much water out. Whatever part of his body was immersed in the water, that much came out. And that's where the term eureka. They make the claim that he ran through I think it was Syracuse, ran through the streets of Syracuse so excited, without any clothes on, saying, I found it. Eureka. That's where the word eureka comes from. It's not really pronounced right. It's eureka. So that's the story behind, I don't know if that's true or if it's legend. My own father told me that story, and one of the great physicists that has been associated with this great university, Dr. Friedman, had told us that story too when we had a class about this. So I think we hear that we see this in the books too as well. So that's the story that goes with that. I think he actually discovered that a king was being cheated by his jeweler as far as the crown. How much was gold? How much was lead? And that did not end well for the jeweler who was caught with what had happened. So this is a lot. This is something here. So is there something to look at here? Is there something to say? Yeah, I think we basically got to this conclusion, guys, a number of ways here. Now you might say to me, Malus, yeah, that's all well and good, but you forgot to put in the atmospheric pressure. No, the atmospheric pressure pressed down here, but that same atmospheric pressure distributed itself throughout this and also pushed upward. So in both instances, if you really want to put it in the strictest sense, you could add an atmospheric pressure to this guy. You could also add an atmospheric pressure to this guy. And P atmosphere minus P atmosphere is 0, and you're back here. In a backhanded way, you guys, we discovered this. What we had done, we were over here. We figured out this is the pressure due to the water. True. What's the total pressure? Well, in actuality, the total pressure would be put the atmospheric pressure on there, plus, and call this guy Y. It doesn't matter what you call it. I mean, it could be Y1, it could be Y1, Y2, H, whatever the depth is. Rho GY, or P equals P0 plus rho GH. It doesn't matter what depth you're at. If you want, guys, what were we doing? We found out what the pressure was just due to the water that was above the cube, either imaginary cube or real cube. We found out what that pressure was just due to the water and the fact that the water was being pulled down by gravity. This is the pressure just due to the water. Add the atmospheric pressure to it, and that's where you get this. I'm going to the front here and get right this one. That's all it was. That's all it was. So these are great formulas. When you're looking at a lot of this stuff, you got this, and as I said, the force buoyant. I mean, there's a lot of ways. There's ways they write it in the book. In the end, guys, this has got to work for you. You got to make sure the logic is there. Your obligation, obviously, when we're doing this, make sure you got the right answer. I mean, that's a kind of a simplistic way of saying it. I mean, I don't care what your perspective is on this. I mean, I respect your perspective. Just make sure that it's realistic, it works, and you're getting the right answer, and I'm okay with that. Forgive me, I should have been a V. That's just what we derived. Okay. So Archimedes Principle and Pascal's Principle. Pascal's Principle will help you prove Archimedes' Principle. That one's born of the other in a sense. If you're proving one, you're basically reaching the other. It's not much of a step to reach the other when you're doing that kind of thing. Looks pretty good to me. They talk about a number of things here, guys, and so let's see what we can say about it. There is, they talk about fluids in motion. Certain aspects of a fluid in motion can be understood by assuming the fluid is non-viscous and incompressible, and that its motion is in a steady state with no turbulence. The flow rate through the pipe is a constant, which is equivalent to stating that the product of the cross-sectional area A and the speed V at any point is constant. At any 2 points, therefore, we have A1B1 equals A2B2. This relation is referred to as the equation of continuity. I'll get to this in a little bit, you guys. 2, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume is the same at any 2 points along a streamline. Say that again. The sum of the pressure, which is the kinetic energy per unit volume and the potential energy per unit volume, is the same at any 2 points along a streamline. P1 equals 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. This equation is known as Bernoulli's equation. Solving problems with Bernoulli's equation is similar to solving problems with the work energy theorem, whereby 2 points are chosen, 1 point where a quantity is unknown, another where all quantities are known, and then solve for the unknown quantity. So let's get there, guys. Let's talk a little bit. Let me see what I'm going to say here. I mean, again, you guys have, in this particular regard, in some ways, I guess, you got a little bit of an advantage. I always love the live presentation when I got people in front of me, guys, but we got it here. People can always photograph it. Here, I guess, on the film, you can stop the film and go back to it. So we got all this stuff. We got here, guys. I think it looks pretty good. I think I'm gonna erase. So all of this is we got here. I'm gonna erase all of this and then start on the front board again, and then we'll talk a little bit. I think so. So that's okay, you guys. You got me, and you can always go back with the film and see where we're at. I think we're looking pretty good. Looking pretty good. And we'll kind of, like I said, we'll maybe summarize a little bit. toward the end. That's not a bad way to go either. We'll see. At least it's all up there for us. Okay. So, this two-handed erasing technique has been perfected over 30 years of teaching. Okay, don't try this at home, ever. So, this kid. All right. All right, guys. Some stuff they talk about. Let me see what I can do. I'll do the best I can. I think we're okay. My goal is to get through 9 today, and I think we're good. We're good to do that. So when we do something like this, you guys, we can say a bunch of things. Talk about continuity and everything else. They're trying to, you know, they talk about turbulence, viscosity, things that we're really not going to talk about. We're not going to be talking, I mean, there's kind of the analogy to friction when we are pushing something across. I'm pushing something across the cement and there's a lot of frictional force. I'm pushing this thing across the floor, this box across the floor, straight across the floor, and there's a lot of frictional force going on there. So, you know, the viscosity and turbulence are sort of the analogy to that when you find the flow of fluids. We're going to assume it ain't happening here. The stuff is incompressible. Even when it's not incompressible, even when it's just airflow, Bernoulli's equation tends to work. Exactly to what degree, perhaps that's subject to debate. I've read stuff about it regarding Bernoulli's equation and stuff, but it tends to work. To exactly what degree, that's perhaps subject to some kind of debate. But for a lot of the problems we can do, even when we're talking about airflow, Bernoulli's equation is useful to us very much, even though air is clearly not an incompressible fluid. We're talking about water. We're going to assume there's no viscosity, none of that, no turbulence, there's no analogy to friction there. And let's talk about it. What's going on here? Let's say there is, there's a lot of things to say, guys. I don't know how much time I got to say it, so I'll try to kind of that's a cross-sectional area of A2. You know, and that's the same thing. That's also A2, let's say. But, you know, this doesn't look like it. Trying to think how I want to talk to you about this. I'll say it like this. Just want to make sure I want to kind of make this pretty obvious. This is also A2. And this thing went L2 distance in time t. The water's flowing in here. actually quite fast. This one right here, all of this stuff is kind of like set in stone, guys. The big thing is understand what we're doing. Make sure this is making some kind of sense. We got this guy right here. That is about the worst drawing I've ever made. Put one right here. And let's say that's L1 in time t. And the flow here, it ain't that fast, but there's a lot of it. Here it's real fast, there ain't a lot of it. And I'd like to know what's going on there. There's flow coming in, and there's flow leaving. Whatever. It's a cross-sectional area of the pipe, you guys. We're trying to figure out what's going on. So with that in mind, well, that's what's going on. I just told you, for our purposes, there's no, just for the sake of the argument here that we're making, there's no fluid flow analogy to friction here. There's no turbulence, there's no viscosity, it ain't gonna be an issue. The reality is, it is an issue, but they can limit that, and that's where a lot of stuff comes into play, where engineers do stuff to try to limit things. But for our purposes, we're just going to do the mathematics. We're not going to worry about it from there. We've got this. We've got this. I got to talk to you. There is a source that is putting forth pressure, that is pushing water, and the water is flowing at a particular rate of speed. Yeah, it depends where you are, man. Water flows a lot faster if it's in a constricted situation. Depends what we got going on here, how we're actually doing this whole thing. But we'll say that there is a power source. There's a power source over there to your left that's pushing this water through this pipe, through this hose. And some crazy stuff happens with this hose. It's really big in some places. It's really broad in some places, and it's very narrow in other places. It is, so there's a great diameter in the hose in some places, and a small diameter in the hose in other places, and the water's flowing through. Here's a simple thing to remember. Whatever fluid goes into this hose is the same amount of fluid that comes out of this hose. Whatever goes into the hose is the exact same, whatever amount goes into the hose is the exact same amount that comes out of the hose. At the end of all the story, and there's a lot that goes on, and we're not going to go into all that right now. There's a lot that can go on, there's a lot of things we got to keep in mind. This is a lot similar to what happens with electricity. When they talk about electricity and magnetism, when we talk about the flow of electricity, there's an analogy even here. Very much so. That's not our business right now. Our business right now is this. Whatever amount of fluid comes into a hose, whatever amount of fluid is going into the hose, that same exact amount of fluid comes out of the hose. I don't care how the hose is shaped throughout the journey. I do know that when there is a very, very great amount of cross-sectional area, the water, I'll say water, I can say fluid, I can say a lot of stuff, let's say water. In this particular case, the water flows slowly. Why? Because there's just a large area. There's a large area. When it narrows, the water has to speed up to keep the same volume flow rate. A lot of times what they do is, they say, and this right here, this cross-sectional area, is A1. All of this took place in a time t, and here, it took, for a time t, it went this far. Here it went this far. What does that mean? Well, guys, I'm not much like a fool. But the last time that I checked, if something goes a very great distance in a given period of time, and something else compared to it goes through a much smaller distance in that same period of time, one of them is going much faster than the other. If one goes 10 times further distance in the same period of time as the other one goes, on average, its magnitude of velocity is 10 times greater. On average, its magnitude of velocity is 10 times the size, the magnitude of velocity of the other. So are you trying to say here, this is what T also, can we say that V2 is L2 over T in terms of speed of flow. And here we'll say that V1 is L1 over T. Okay. Great. What am I talking about? They frequently use, I know Q gets used in heat phenomenon, so you gotta watch out a little bit. Watch out a little bit when we're doing that stuff. Can get used in heat phenomenon. So I'm not talking about heat phenomenon right now. I'm talking about Q for quantity of flow. Q for quantity of flow. The mass flow rate. Remember, if this thing's got, if the fluid in here is water, or it's some other fluid X, or fluid Z, or fluid Q, or whatever, I mean, some fluid. It could be liquid mercury. It could be mercury. It could be ethyl alcohol. It could be liquid gold. Whatever, it could be oil. Or literally liquid gold too, not oil. Oil also is liquid gold, sometimes they call it, right? I mean, it's very expensive, but you guys understand that rho is mass divided by volume. Mass is rho times volume. Ladies and gentlemen, if the density of the fluid doesn't change, we said it's an incompressible fluid. You're not compressing it. You're not going to make it more compact. You're not going to make it less compact. Its density doesn't change in plain English. M equals rho times V. What's V? V is the volume of the flow. The volume of the flow is identical at the beginning, the middle, and the end. I don't care what it's going through, how broad the hose is at that point, how constricted it is, or how intermediate between the two it is. It doesn't matter. The volume that flows through it is identical in all instances. Q equals Q. Q1 equals Q2. What does that mean? That means, well, okay, it's the volume flow, it's the mass flow rate, the volume flow rate. I'll make a long story short. There is the same amount of mass per unit time that goes through each of these. I know, what are you talking about? Well, I'm saying right here it's flowing real slow. It's flowing real slow right here, but that volume is the same as this volume. The volume through here, the volume here, and the volume here are equal. If the volumes are equal, the masses are equal because the density remains unchanged. So it's looking something like this. Now the way they wrote it is, that's it, the masses are the same. I want you to remember that, because when I go to Bernoulli's equation, I'm not going to have to talk about it as much. You've already seen me do it. What the heck, we got this far, let's just do it. Rho V over T equals rho V over T. That's what this is. If I divide by rho on each side, let's talk. I mean, let's talk a little bit. This is volume 1. This is volume 2. I already told you the volumes are the same. The volume flow rate is the same. If you divide by rho on each side, you're getting what I'm getting here. Well, A1 is a big area, you guys. This is volume, it's not speed. I'll get to speed in a second. These are volumes. Volumes. V is something different. I mean, V for velocity. Got a question to ask you. Is A1 times L1 volume? Is A2 plus L2 volume? Simple question. It is and it isn't. I mean, we got to visualize it first. I mean, it's not. You know, I don't think. I'm really. I guess I've had arguments with former friends, I guess, about what's obvious, what isn't sometimes, and philosophical issues or something like that, right? A lot's not obvious, right? I mean, that we know a long time ago, a very long time ago I'm talking about. But what I'm trying to say here is this volume right here, you guys, is volume V1. This volume right here is volume V2. It's not small v2. It's volume I'm talking about. These are volumes. These are velocities. Okay, we know a lot. Can I ask you a question? If this is A1, and A1, if this is A1 and A1 is constant, if this is area A1 and it's constant and it's displaced by L1, area times length is volume. If this is A2, and it's displaced by a length L2, A2 displaced by a length A2 moving through a length L2, A2 moving through a length L2 is volume 2 is A2 times L2. Volume 1 is area 1 being displaced, being moved through a length, taken through a length L1. Volume 1 is V1 L1. Ladies and gentlemen, this is what I'm saying right here. What do you say you write this? Okay. Last time we checked, guys, as far as an average velocity is concerned, it's simply this. Length traveled divided by time. And that's what they're getting this conclusion. V1 is magnitude of velocity equal to L1 divided by T. V2 is magnitude of velocity, which is equal to L2 divided by T. This is the continuity equation. Pretty useful. If you multiply this is volume flow rate. If you multiply volume flow rate by rho on each side, it's mass flow rate. Total mass equals total mass. Rho A1 V1 equals rho A2 V2. Per time. Forgive me, per time. Because this is per time. This is volume per time. So, there's a lot here, guys. You gotta look out for the symbolism. Symbolism can change quite a bit. The mathematical realities don't change. Just gotta kind of watch your step. Watch your step when you do this stuff. So that's good. I mean, it's good for us, man. It's going to work for us. They got this thing called Bernoulli's equation, and I'm going to use what's up here to make it work for us. We have it up here. Just trying to debate a little bit how I want to take this thing. How we want to talk about it. I guess I'm going to leave that up there. I'm going to go to the other board, and then we can always come back to it a little bit, maybe if we need to or something like that, just kind of as a reference. We'll see how it works out. They got this thing called Bernoulli's equation, and a number of ways to look at it. Trying to figure it out. And again, I've got this covered pretty decently, guys. I mean, I got about, just in the Serway book, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. About 26 problems on this stuff, on the chapter 9 stuff. And I only did a couple on film, but the rest is in Canvas, as we said. And that's a lot of what's going to be going on, guys. So just kind of be aware of that. And do great. You guys are going to do great here. Let me look at some stuff I had done here. I used actually another book on one of these things I'm lecturing on, but it's the same exact equation, you guys. There is stuff we've talked about to get to where we got. I'm just trying to debate here. Just to play it safe, I'm going to leave it up there, just to play it safe. The last thing people want to do is see me do this for 20 minutes more, right? I mean, so let's keep it there. Let me go over here and let's come back. I doubt I'm going to need it at this level, but let me just start over here, come over here, and let me raise that a little bit. We'll see what we can do. There's this thing, I just want to make sure they're speaking the same language. I took this out of another book. It was a calc-based book, but it's exactly, yes, it's verbatim. It doesn't matter. The difference in terminology is kind of trivial. The mathematics is identical. Well, these great mathematicians, the Bernoulli family, their brothers, or the dad was involved. I don't even know. Maybe even there's just a lot of people in this family. There's just some tremendous mathematics. And this is some of the mathematics that they did. Some of the talk that they made. Regarding this stuff, you guys, there's this thing called Bernoulli's equation, and named after one of the people in the Bernoulli family, and Bernoulli's equation, and I'll write it down and then we'll talk about it. Pressure 1 is 1/2 rho v. I'll write it down. We'll talk. Okay, it's a lot there. It's not that bad. Trust me, it's not that bad, what I tell you. It derives pretty easily, surprisingly so, I guess I can tell you. This is Bernoulli's equation. And what is it? Well, you know, I went from, I looked at what another professor, another author had done in another book, the calc-based book that we use for 209, Dr. Deborah Katz. And she says here, as Dr. Katz tells us, and I'm quoting her now, Bernoulli's equation is a statement of the work energy theorem for ideal fluid flow. I'll try to, I got, this is, everything I'm looking at right now, guys, in my hands, all of this, and again, I know I beat this into the ground pretty solidly, I guess, at this point. I will continue to beat it into the ground, because it's for real. What I'm about to show you is on Canvas, word for word. You've got access to this document, look at it if you wish. This is what we're looking at. Rho is the Greek letter with an R sound. Rho is the Greek letter for the R sound. This is P. I know they look a lot alike, just be aware of it. The guy in front, P1, and the guy in front, P2, that's P. The other ones are rhos. Means density, it's mass density. What is going on here? Well, there are numerous other ways to write this. They say some stuff here. It's a restatement of the conservation. This is a restatement of the conservation of energy that you guys have already seen before. You've seen me talk about it on film. You've seen it in the book. You're either going to see me do it, or if you look at the film, you know, you've seen it on film, you've seen it in the book, you've seen it in the problems. This is actually a restatement of the conservation of energy. But they divide by volume on each side. Basically, just like we say mass density, rho, is equal to mass divided by volume, mass density, rho, is mass divided by volume. Energy density is energy or work divided by volume. This is a statement of the conservation of energy, only dividing by volume on each side. So it's volume density that you're talking about. If you multiply by volume on each side, you get back to the conservation of energy. You take the conservation of energy, you set up an equation, and then you divide by volume on each side, and you get Bernoulli's equation. It's as simple as that. In Bernoulli's equation, we talk about energy density or work density being conserved. So there's stuff they do. Let me see. I wrote this here. I'll end up writing it again. Let me get rid of some of the stuff here. Let me stay here on the front. Let me stay on the front board. Let me leave that up there for a bit if I have to come over a little bit again. But we'll see. For right now, we got Bernoulli's equation. Let's talk about how that actually comes about. Looks pretty good. I'm just debating what I'm going to erase here, guys. No big deal. You guys already have it. I'm gonna hit it. This, this should be of great interest vis-a-vis this stuff. I think we're good. I'm gonna erase it. Remember what we did here, guys. It's going to be useful as we talk about Bernoulli's equation. I think it's just going to go. I think it's a good idea to just take this and take Bernoulli's equation kind of from the start. But at least remembering the stuff we did so we don't have to rigorously define and prove everything that we've already, hopefully somewhat rigorously defined and proved already. All right, guys, where are they going with this thing? Well, they're taking that tube I talked to you about earlier. They're taking that same tube that I just talked to you about and I just erased. And then they did something, they kept that and they kind of did something else to it. They picked up one end of it and kept the other end lower. And they said, okay, let's really throw a wrench into this thing. Let's really challenge these guys as to what's going on here, how this thing's gonna flow and how this thing's gonna play out. So with that in mind, okay, they say, book said what it said. I think I'm going to stay with the notes straight out with the notes. We have said, remember there was a flow going on in that first pipe, in that first pipe system, in that first hydraulic system, in that first system involving the flow of fluid. We knew that at the end of the day, the mass flowing in a given period of time, is equal to the mass flowing in a given period of time. The volume flowing in a given period of time is this. Observe, equal volumes of fluid V of equal masses. So observe, equal volumes of fluid V of equal masses M. The masses are equal in a given period of time that are flowing through at any point on the pipe. The pipe may be 10 kilometers long. At point 1, the flow rate is this. At point 2, 10 kilometers down the road, it's also the same this. The mass flow rate and the volume flow rate are identical in a pipe. If whatever goes into a pipe comes out of a pipe. The same amount that goes in is the same amount that comes out. It's kind of the premise of a lot of what they're doing here. And again, I've got this in color on canvas. Might be easier to look at there. I don't know. Might be. We got to talk a little bit. You remember the last thing I told you? It wasn't going that fast. That's a volume. That's a speed. It wasn't going that fast. This guy is volume V1. We'll call it V for volume. That's speed. Two different things. That's why I'm making one so much bigger than the other. Hopefully differentiate them somehow. The amount of mass that comes through here, the amount of mass here is M. There is work being done per unit time, in other words, power being expended. Work W1 to push, work W1 done to push that mass of fluid, to push that volume of fluid. I don't know how much is one, how much is the other, guys. This is also the same amount of mass. This is also the same amount of volume. In fact, let me draw this. They're the same amount of volume in both instances. There is, by virtue of something, I mean, by virtue of the fact that there's an inertial quality to mass, there's action-reaction, there is friction at some level. Maybe there's some viscosity. Maybe there's something here. There's a little bit of work, there's a little bit of negative work going that way, stopping you. If this arrow looks smaller, this arrow looks smaller than the other arrow, it should, because in the end, all this stuff is flowing this way, to the right. Let's talk some more. I don't know what you could say, guys, right about to the middle or something, right about here to here. On the downside, this is height y1. I'm going to the center of mass. Center of mass of the fluid at any particular point. Here I'm going to go to the center of mass at any particular point. We'll say that's y2. This guy ain't moving that fast. This guy is. Guys, I can't, you know, I know you don't want me to draw this again. We saw what we did last time. We saw how this stuff flows, right? If it's a big cross-sectional area, it flows slowly. If it's a small cross-sectional area, it flows fast. The total amount of mass per unit time is the same in both instances. In all instances, the total amount of mass flowing per unit time is the same. The total volume flow rate is the same at any 2 points. The total mass flow rate at any 2 points is the same. So we got it to here. This distance between these two, this guy and this guy, the difference between these two, from here to here, is the big one minus the small one. Well, I'll tell you what I'm going to do. It's all about work. And then afterwards, I'm going to do a fancy division, and we should be okay. I can probably get this done in the next 10 minutes for sure. This clock's correct, isn't it? Is it correct? Okay. 15 minutes max. I think I can do it, but I need 10. All right. So we're looking right here, guys. Work is work, huh? Yeah, W2 is not as much work as W1. They're fighting each other. W1 is bigger. That one's a negative work, so you can add a negative or just subtract. The difference between the two is the net amount of work that is being done. Yeah, I'll give you an idea what a net amount of work is, you guys. Here, the entire mass is going at that speed. Ain't that fast? Here, the entire mass, spread out as it may be, is still the entire mass, and it's going faster. Yeah, there's something else you got to keep an eye on. Here, this mass is at a low height. Here, the other mass is at a high height. This mass has higher potential energy. This mass has lower potential energy. Low potential energy mass, high potential energy mass. Low kinetic energy mass, high, so low potential energy mass, high potential energy mass. Low kinetic energy mass, high kinetic energy mass. The difference in the two works, there's work this way, I'm fighting you. Somehow there's something fighting him. It's just by virtue of the fluid itself. There's something in there, it's not going to let you move it that easily. Okay, I'll say it's W2. There's something happening here. Maybe there's another flow rate going that way, and there's a flow rate this way, but this guy wins. There's work 2 here, there's work 1 here. So that is, forgive me, I should have called that, wrote it down wrong. Work 1 divided by, work 1 minus work 2 is what we're looking at. What is that all about? I'll tell you what it's all about. It's all about the mass and how it's moving and where it's located, ladies and gentlemen. There is a mass M. There is a mass M. What is that mass M? I'll cross that bridge in a bit. There's a mass M moving at V1. Actually moving at V2. I'm going to go for the bigger one. I know this is a big answer. W2 is small, W1 is big. W1 minus W2, big minus small. W1 is big, W2 is small. Subtract to get a positive answer. Well, wait a minute. My take on this right now, for the sake of argument, is 1/2 m V2 squared. That's a lot of kinetic energy. Minus 1/2 m V1 squared. That's not a lot of kinetic energy. The difference in those two kinetic energies is the change in work that was done partially. You also got to account for potential energy. This guy, the mass at a high height is a lot of potential energy. This is a small amount. Man, we're almost there and we don't even know it. Delta W equals delta KE. That's this. Plus delta PE. Now, for a given delta W equals a constant, then an increase in KE implies a decrease in PE. And an increase in PE conversely means a decrease in KE. I gotta talk to you. What do you say we take all this? You guys got it there. You can always rewind it. What do you say we take all this that's happening for one mass, for one amount of mass called M with volume V? The mass M has volume V. What do you say you take both sides and divide by V? V for volume. That's the delta W we talked about earlier. Okay? Let me actually erase that. You got it up there, we got it, we saw it. And we got to talk. Okay. Let's talk. How do you guys feel about this? Is work one, that's the one that doesn't have, that's got the bigger work. Work one is equal to, if you allow, let's not get blinded, guys, by what is out there. We're not going to get blinded by the forest nor by the trees. Isn't work F times D? Yeah, I think so. It went a distance, and we didn't put an L there. Let's say the distance under consideration here, that it actually got moved, is distance D1. And the distance it got moved here is a lot more. That's D2. How would I say force times distance is equal to work? For the other guy, how about force times distance is equal to work? Sounds good to me. I got more to ask. What do you say you remember that the volume is A1 D1 or A1 L1. I'm using D right now because I use D in the notes. I'm trying to stay consistent with the notes. The volume is A times L, or A times D. It's the same volume for the other guy. It's A2, D2. I don't worry about that. Got a question to ask you. If you take, what is W1 divided by V? Isn't it F1 D1 over A1 D1? Wait a minute. D1 and D1 cancel. What's F divided by A? F divided by A is pressure. F1 divided by A1. Basically what you're doing here is if you divide this by V, and you divide this by V, why am I doing that? Well, I ended up doing it here. That stuff's all divided by V. Wait a minute. Isn't V the same as A1 D1? Then it just becomes F1 over A1. That's pressure. How about here? V is the same now. He's the same. They're equal to each other. We did that earlier. This is A2 divided by D2. F2 over A2, that's B2. The end of this song and dance, ladies and gentlemen. We got this. What is it? What is mass divided by volume? It's density. What is mass divided by volume? It's density. All right, I obviously this is about the fifth time I'm asking the question, what's mass divided by volume, right? I mean, so it comes out to here, guys. I got this. Let's talk. I'll tell you what I'm going to do. Why don't you add a positive P2? Why don't you add a positive P2 on each side of the equation? And why don't you add a positive 1/2 rho V1 squared on each side of the equation? And also add a positive rho GY1 on each side of the equation. When you do that, come over here with me, guys. When you do that, you get Bernoulli's famous equation. Very important. I have this done in detail on campus. You guys. All of this is obviously Bernoulli's equation and statements pertaining to conservation of energy in one way or another. There's this fountain problem. Maybe we'll do it the next time. Probably not. Probably go to. But there's an interesting fountain. There's an interesting fountain problem in the notes that I have on Canvas for you. I suggest that you look at it. Looks pretty good. So here it is. That's it. If you just rearrange the terms of what I just did over there on the front board, you get what I have over here on the sideboard. You get Bernoulli's equation that I wrote at the very beginning of the discussion pertaining to Bernoulli's equation. That is it. Thank you very much for your time, guys. I appreciate it. Good luck to you.